everyone, Katrina here, and today I'm going to show you how to use trig subs to solve a challenging integral. Make sure to watch to the end to see the full solution, and please subscribe for more videos. Let's dive into this problem. So in my previous videos, I talked about the different cases, the three cases actually, where you can do trig substitutions. So be sure to watch that video if you need some background. Today we're going to go straight in to an example because it's going to take a little while to get through this one, but make sure to keep watching because it's an exciting one. So here we have the integral of x to the power of 5 multiplied by the root of 4 plus x squared, and we're integrating with respect to x. So whenever we have these integrals that have usually like square root signs or weird powers, we want to think how we can use trig substitutions. So I'll give you a little hint. So if we have functions that contain the form a squared plus x squared and the root of all of that, we can usually try the trig substitution such that x equals to a tan theta. And we have to remember the caveat for this one, such that our theta is bound between, it's not equals to, it's just in between because there's asymptotes between negative pi over 2 and pi over 2. So it looks like we have this kind of form over here, where in this case our 4 is our a squared. So if 4 equals to a squared, then that means that we'll let our a equal to 2, and then we can try our substitution over here. So we would, in this case, let x equals to 2 tan theta. So now that we've done that, that's kind of like the housekeeping of our problem. We can dive in and try to solve this problem. So let's go right ahead and plug this in. So the one last thing I just want to tell you before we start is we just want to recall some trig identities. So just recall over here on the side that 1 squared plus tan squared theta, this equals to secant squared theta, and also that that's the same as writing it generally, that a squared plus a squared tan squared theta is equal to a squared secant squared theta. So just keep this identity on the side of your paper because we'll see that we might have to use it pretty soon. Okay, back to our problem. We're going to go ahead and do our substitution. So we now have then the integral of 2 tan theta to the power of 5 multiplied by the root of 4 plus 4 tan squared theta, and then we also, since we did our x substitution over here, we then have to figure out what our d of x is equal to. So we found our x value, so let's go find our d of x. So if x is 2 tan theta, then that means dx equals to 2 secant squared theta d theta. And we know that because the derivative of tan is equal to secant square. So because of that, we then have to add that in over here. So then we have multiplied by 2 secant squared theta d theta. Okay, let's go ahead and work on simplifying this. So we now have 2 to the power of 5 because we can expand this 5 to apply to both terms in our bracket. So we have 2 to the power of 5 multiplied by tan to the power of 5 theta. Then all of that is multiplied by 4 secant squared theta, and that's thanks to our handy dandy trig identity, which I pointed out to you over here on the side in red. So that helped us out. And then we have our last bit over here, which is 2 secant squared theta d theta. Okay, So what's next? So now we can work on simplifying this piece over here. So we're going to take the square root, but we want to take the positive square root, so we're going to have to put it into absolute values. And when we take the square root here, the square root of 4 is 2, so we're going to add an extra 2 over there, so it's going to be 2 to the power of 6, and then 10 to the power of 5 theta, and then over here we're now going to have the absolute value of secant theta, and then multiplied by 2 secant squared theta d theta. Okay, so is everyone clear what we did over there? So we took the square root here, the square root of 4 is 2, and following our exponent rules, we added in the exponent here, so we now have 2 to the power of 6, and then we took the positive, the absolute value of our square root. So that's why we have the absolute value of secant squared over there, and we left this last part here the same. Okay, let's keep going. Good job, everyone, for following along. Okay, so now we have another 2 right over here. So let's go ahead and add that up here. So now we have 2 to the power of 7, okay? Then we have still 10 to the power of 5 theta, and then we've got, what do we have here? We've got secant theta multiplied by secant squared theta d theta. And the reason why we can do that is, remember that we set the specific bounds for theta, and within those specific bounds our secant is going to be positive. That's why we can take this piece over here in the absolute value and then simply end up with just secant theta. Okay, so now we're going to start taking things out of this integral that we no longer need, or that we know are constant and are not dependent upon. So in this case, we can see that theta is a value that we're integrating with respect to. So that means that this 2 to the power of 7 that we see at the beginning is a constant value. And since it's constant, that means that we can actually remove it from our integral and put it onto the outside. So that means we have our 2 to the 7 on the outside there, and then multiplied by the integral of 10 to the power of 5. And then since these two secants are the same base, and they're multiplied to each other, that means we can add their exponent. So as a result, we have secant cubed theta d theta. Okay, let's keep going. So we now have 2 to the 7, and then multiplied by the integral of, what do we have here? We can have 10 to the power of 4 theta multiplied by secant squared theta, then tan theta, secant theta, d theta. So here we're applying, what are we doing here? So here we're just separating it out. So instead of having 10 to the 5 here, we are separating it out so that we have it in this sequence, so that we can cleverly apply an algebraic trig and trig identity. Okay, so next up, we've got 2 to the 7 multiplied by the integral of secant squared theta minus 1. We're applying our identity, all squared, and then multiplied by secant squared theta, secant theta, tan theta, d theta. Okay, so now we're going to apply a u-substitution. Okay, so we're going to say let u equals to secant theta, and as a result, our du equals to secant theta tan theta d theta, because the derivative of secant theta is secant theta tan theta. Awesome. So now that we have this substitution, we're going to plug that in to our integral up here. So after we plug it in, we get 2 to the power of 7, and then the integral of u squared minus 1 all squared times u squared du. And this looks much friendlier. So you can get a little smiley face there. Okay, so now what can we do? Well, let's try to expand and simplify. So we've got 2 to the 7, and then we can expand this expression here so that we have u to the power of 4 minus 2u squared plus 1 all multiplied by u squared du. And this actually simplifies quite nicely. So what we're going to do now is we're just going to take this u squared and just distribute it into our integral over there. So after we do that, we get u to the power of 6. Here we can just add the exponents, minus 2u to the 4 plus 1u squared all du. Okay, and this is really easy to integrate. We can just use the reverse of the power rule to integrate this expression. So that means we now have 2 to the 7, so we'll keep this on the outside and integrate each one of these. So that means we've got u to the 7 over 7 minus 2u to the 5 over 5, and then plus u to the 3 over 3. And then remember, we always need to add our integration constant because we do not have integration bounds here. This is an indefinite integral. Okay, we are not quite done yet. We have to express our final answer in terms of x. So we'll write that. So final answer with respect to x, because that's what we started with. So that means we have to go back and kind of undo our substitution. So let's take a look at that. So that means that x is equal to 2 tan theta. So that's what we started with, right? X equals to 2 tan theta. So how can we get a value for theta? So let's go ahead and rearrange this. So x over 2 equals to tan theta. And now we need to take the inverse of this to find theta. So taking the inverse, we get that theta equals to tan inverse, or we can write it as arctan of x over 2. Okay, so now that we have this value over here, we have to then apply it into our function. So now we have theta with respect to x, but we also have another substitution that we have to undo. We recalled our u-substitution over here. We said that u equals to secant theta. So that means everywhere we see a u, we have to put our secant theta. So let's show that over here. So we have that u equals to secant theta. That was our first substitution. So we're going to do this one first. So we're going to apply this substitution back into this answer where I showed the arrow. So as a result, what do we get? We have 2 to the power of 7 times secant 7 theta over 7 minus 2 secant to the power of 5 theta over 5, and then plus, what do we have here? Secant to the power of 3 theta over 3, and then plus c. Okay, first substitution done. Now let's go ahead and do this substitution right over here. So we have to put that back in. And what do we get there? We get 2 to the power of 7 all multiplied by secant 7 to the power of 7. Then where our theta is, we now have arctan x over 2 all over 7. Then we have minus 2 secant to the power of 5 of arctan x over 2 all over 5. We're going to need some more space here. Hang on with me, we're almost there. And then we have secant to the power of 3, then arctan x over 2, all over, what do we have here? All over 3. And then recall, we still have our integration constant, which is c. Okay, so technically this is the final answer, but we can do better than this. We can further simplify this. So we can actually take a look at this arctan x over 2, and we can see how we can use that to simplify this. Okay, so let's look at the term secant, and then in brackets, arctan x over 2. How can we simplify this? Well, this is actually really cool. We see that it's tan x over 2. So this ratio over here actually helps us to make a triangle. So we can simplify, oh my goodness, I can't talk and spell at the same time. So we can simplify this expression using our SOH CAH TOA. So this is our nice trig rules that we can use to simplify this. So again, like I said, this ratio allows us to make a nice triangle, which will help us simplify this whole thing. So let's look at what this triangle may look like. So we see that tan theta equals to x over 2. That's what we got from this arctan piece, because we undid the inverse, so tan theta equals x over 2. And if we follow SOH CAH TOA over here, we know that this equals to our opposite over our adjacent. So if we draw out a triangle, let's draw out a little triangle over here, that's right angle. We would have our angle theta over here. So then our adjacent value here is going to be 2. Our opposite value is x. And following Pythagoras' theorem, we see that our hypotenuse of the triangle is going to be the square root of 2 squared plus x squared. Okay, so, well, how does that help us? It's actually very important. That actually means that our secant of arctan x over 2 is equal to what? So secant, the reciprocal of secant is cos, right? So 1 over cos theta equals to secant theta. So on the side, we know that cos theta, following Pythagoras' theorem, equals to adjacent over hypotenuse. So that means that secant theta equals to hypotenuse over adjacent. And this is a triangle that we're considering here. So you can kind of think of this whole piece over here as our theta, which we have right over here. So we can use this triangle right over here, which is amazing. So that means that our secant theta equals to hypotenuse over adjacent, which is equal to the root of 2 squared, which is 4, plus x squared, all over 2. And now that we have that, we can then just plug that back in to our integral over here, and we can get a much more simplified answer. So let's go ahead and do that so that we can have the best answer possible. So we now have 2 to the power of 7 in brackets. We have 4 plus x squared to the power of 7 divided by 7 times 2 to the power of 7. And then we have minus, minus 2, and then we've got root of 4 plus x squared to the power of 5 divided by 2 times 2 to the 5, and then finally plus the root of 4 plus x squared all to the power of 3 over 3 times 2 to the 3. And remember our integration constant. And one last step. Okay, we can do this. So our final answer is going to be 4 plus x squared to the power of 7 over 2 over 7 minus 8, 4 plus x squared to the power of 5 over 2 all over 5, and then plus 16, 4 plus x squared to all to the power of 3 over 2 over 3 plus c. That deserves huge smiley face. Good job, everyone. We made it to the end. So it was a bit of a lengthy process, but it's not too difficult once you use the trig substitution. Using the substitution allows us to apply different trig identities and simplify this. You saw that this was also a bit of a hybrid problem, so not only did we use trig substitution, we also had to use a u-substitution, which really helped us take the integral. And then always remember that before you think you're done, well, add the plus c, but then also make sure that you're going back and you're essentially undoing those substitutions so that you end up with the correct variable in your final expression. So for our final expression here, we need it to be with respect to x. That's it for today. If you enjoyed this video, please give it a like and comment any questions that you have. I'd love to hear from you, and I look forward to seeing you next time.